Okay, so for those of you guys who are listening in on the recording right here, what we're doing is I'm going to talk about a Webassign problem. So here's the Webassign problem. The first problem right here, this is dealing with our Chapter 8 confidence intervals. And we're asked, well, let's suppose that an accounting firm does a study to determine the time needed to complete one person's tax form. Well, it randomly surveys 125 people. So the sample mean is 22.9 hours in this example, and there's a known population standard deviation of 6.2 hours. So the population distribution is assumed to be normal right here. When we're dealing with this, then what we're going to be dealing with is a normal distribution. That's actually almost a given right here. So in a lot of these problems, you'll be told it's that. Sometimes you're not, and we have to figure it out on ourselves here. And I'm clearing up the chat box here, so you guys, if you have a question, you can stop me and I can bring it up. But we say, all right, well, what's our mean? Well, we're told the sample mean in this case is 22.9 hours. So we just go ahead and enter that one. The standard deviation, well, this is the population standard deviation, sigma, and we're told that it's 6.2 hours. So we're just going to go ahead and enter that number. And n represents our sample size. So our sample size, we're told we're serving 125 people in this survey. So all we're really doing is just accounting for some of the basic information. So what we need are some words to define what it is that we're actually doing right here. So we're dealing with the random variable x. And the question is, well, what is the random variable x right here? And we can see that it says, well, determine the time needed to complete one's tax forms, right? And it gives these sample times in hours right here. So what we want is probably something that tells us that it's a time that's required, and it looks like these first two choices to give us time for hours, to complete one person's tax form. So that's what they said in the statement above. And x bar is the mean time to complete the tax forms for a sample of 125 customers. Or x bar is the time needed to complete one person's tax form. X is the mean time needed. Well, our mean time is x bar. Right, so we say x bar is a mean time right here, needed to complete the tax forms from a sample of 125 customers. So it's really got to be this first one right here. That's the only choice that makes sense. We're not dealing with the number of tax forms, and we're not dealing with, you know, the number of tax forms and the mean number of tax forms. So none of those fit. The only one that does right here is that explanation. All right, so which distribution should we use for this problem? Now, in this case, actually, let me go back to my spreadsheet, because this program, this spreadsheet program that I'm using, actually gives you a little bit of information on that at the bottom when you scroll through. All right, so when do we know to use? We call this the one mean z interval procedure. That's what I call on this program. Basically, how do we know when to use a normal distribution? And the answer is that if we know the sample size, right, we've got small, moderate, and large samples. Well, a small sample is less than 15, moderate size samples from 15 to 30, and a large sample is size 30 or more. Well, guess what? We've got a large size sample right here, right? Our sample size is 125 customers. So we're definitely in that last category there for large samples. And it says this Z interval procedure can be used without restriction. So it talks a little bit about the idea of outliers. An outlier is, of course, a piece of data that is very high as compared to the others, or very low. And if you go through and you actually do something like a histogram, or you go through and you look at a distribution table and you look at the values that you get, generally speaking, you can really tell when you've got a very high or very low set of numbers, because they always attract the mean to one side or the other. And you would see that the mean might be very high as compared to the median or the mode if you have an outlier on the high side. But in any case, okay, we're not given that kind of information. We just know that we've got a pretty large sample. So in this case, that's what's going to work. So what we're going to say right here is that we're going to deal with a normal. So we use n. That's our distribution. So x, we read this notation, x bar is in a normal distribution. The normal distribution is going to be a mean. And that mean is, we said, what did we say it was? 22.9 hours, right? So we take the sample mean to be the same thing as our population mean of the samples of size 125. But for the standard deviation, that's the number that comes right here, that's where we're going to have to use our central limit theorem. So we have 125 people in our sample, and the standard deviation is 6.2 hours here. So let's go over here. Let's just calculate this. We have 6.2 hours. We have 125 people, right? So we're going to take the square root of 125. And the standard error of the sampling mean, that is the standard deviation of the sampling mean, is equal to the standard deviation of the standard deviation divided by the square root of the sample size. So I'm just dividing those two numbers right here, and 0.55454. So 0.55, 2 decimal places, is what I'm going to put right here. Let me check that really quickly here, because I just want to make sure I'm telling you the right thing. Yes, okay. So the question is, of course, below that, let's explain your choice. Either we're using the student's t. Well, I haven't talked about that, but the student's t distribution is what we use if we have a small sample size or we don't know the distribution. But we're told this comes from a normal distribution. So it's either the standard normal distribution from the second or third choices right here. And in this case, I would say that this normal distribution should be used. The population standard deviation is known. So that's really our choice right there. All right, part D. Now we're going to construct our 90% confidence interval, and I'm going to describe this diagram right here. If we're looking for a 90% confidence interval for the population mean, what we're going to do is oh, you can only see the PowerPoint? Wow, okay, I mean, you guys can't see the Webassign anymore? Were you able to see the Webassign, Nina? There it is. Okay, so you've got the Webassign now, right? Okay, sorry. Yeah, it sort of went back and forth when I switched screens right here, I think, maybe. All right. So now I'm going to describe this. Okay, so we want to construct a 90% confidence interval about the mean for completing our standard forms. And so we have these numbers right here that we're going to use. The normal distribution with a mean of 22.9 and the standard deviation, right? We're using 0.55. Now in the program, let me go over here in the program. You guys see I've got Excel up, right? My Excel spreadsheet. Nice, okay. So we said the mean was 22.9. And the population standard deviation, by the way, we know it's 6.2. We're actually using the given one right here in the program because in Excel, this automatically accounts for that kind of thing. All right. So in this case, we're going to get the 90% confidence interval in my example. All right, so how do we get that? Well, what we're going to do, we're going to get the confidence interval. The function that we use is confidence.norm, right? That's actually up here in this box. But I'm going to put in the numbers right here. For confidence norm, first of all, the first number you put in there is called your alpha number here. And I'm just going to type in the function just new here. Confidence confidence.norm. Right? So in Excel, this is the function that does it. And the first number to ask for is the alpha. Well, the alpha number is going to be the number that we get by taking 1 minus our confidence level. So we have 90%, so we're going to take 1 minus 0.9. That's 0.10. That is considered our alpha number. Okay. So what you do to get the alpha number is that if you're told it's a 90% confidence level, take 1 minus the decimal form of your confidence level to get this. The second number we're going to put in is our standard deviation. So I'm just going to click on the cell that contains it, but it's 22.9 is what we would enter right here. I'm sorry, the standard deviation. That's not B2. My apologies. It's B3 right here. And then the sample size, and our sample size is 125. Right? So in Excel, this is automatically going to calculate our value right here. And our value, good Lord. See, this is what I get for doing some earlier programming right here. The confidence level is going to be found by taking the mean and subtracting that standard, that MBE. And the upper level right here is going to be the mean plus this margin of error. So plus the margin of error. And these are our upper and lower limits. Right? So going to Canvas right here, we say, well, let's state the confidence interval and round our numbers to 2 decimal places. So for a 90% confidence level, we're stating that the lower level would be somewhere between 21.99 hours. And on the upper level right there, 23.81. 23.81 rounded. Right, so these are the numbers that we want to build our confidence level. So far, so good, guys? I know I'm taking a little bit of time to get this through this video, but here I'm going to try and rush our way through. Okay, we want to sketch the graph. Well, here's what they're actually asking you to do if you're asked to sketch this graph. First of all, our alpha level. Remember that our alpha level, and I'm going to go up here and I'm going to say if we want alpha, right, the alpha is equal to 1 minus whatever our decimal form of our confidence level is. So in this case, my alpha is going to be equal to 1 minus 0.90, which is what I put in there. But remember that we're going to take half of that. Oops, 1/2. So 0.5 times that confidence level, that alpha number. What we're saying right here in this diagram is that, okay, if our alpha is 0.1, half of that lies to the left in this region under the normal curve, and half of it lies to the right. So 5%, there's a 5% chance we could be too high. There's a 5% chance we could be too low. Overall, there's a 10% chance that we could be wrong. What's left? Well, there's a 90% chance that our confidence level is contained within that interval. And that interval, again, is defined by the numbers that we just put above, 21.99 and 23.81. Right? And our error-bound mean, well, that was the number that we found here in Excel. Right here, 0.91215. That is the 90% confidence level. So it says to 2 decimal places, 0.91. That's the number that we want right there. All right, so just checking my work right here. You see what I'm talking about right here. Okay, so far so good. Makes sense? Hopefully you guys have. Nice. Okay, cool. It seems a little weird to do it this way, but hopefully using the Excel is actually a really nice tool. All right, well, the rest of the questions right here, we can just kind of wrap up then. Okay, alpha. Well, okay, it depends on the confidence level. When we say a confidence level, and here's our slide on that, what we mean by that. Let me go back to this. The alpha level, let me go back over here, our confidence level is based on what we call our confidence coefficient, right? And basically what we're saying is that, well, if we want a 90% chance that our mean is contained between these two values, then we're saying that our confidence interval is 90. Here, I'll type this in up here. I'm going to type this in on the board. Our confidence level is 90. I'm sorry, is 90%. So 0.90. But what we want is our alpha level. So confidence level is defined below as being 1 minus the alpha number. Right. So I'm just switching that around. Oops. What I'm saying is that we're taking 1 minus 0.10, pardon me. This is where I'm getting that, right? That alpha number, 0.90. All right. Right, so alpha is the percentage that we're wrong. Right, so if you go into the sketch here on this, right, you see that what it's saying is that the area right over here to the right, the area right over here to the left is half of that 10%. That's where those 0.05s are coming from. All right, so to wrap this one up, it says, well, if the firm wished to make it to increase its level of confidence and keep the error bound the same by taking another survey, what should it change? Well, should it increase the number of people surveyed, or should it decrease the number of people surveyed? Well, if we wanted to increase the level of confidence but keep the error bound the same by taking another survey, we should probably increase the number of people that are surveyed. And the reason why is that as we increase that number of people, the number of the confidence level will decrease, I guess. If we so we're saying that, okay, we're taking confidence level and we want to keep it within that. I think that we would increase these. And if the firm did another survey but kept the error bound the same and it only surveyed 49 people, what should happen to the level of confidence? Well, in fact, right, if we did that, then our error bound the same, right? We only surveyed, what would happen? We'd have to have a larger confidence level to account for that difference, right? Because that we're taking the standard deviation, dividing it by the square root of the sample size, so decreasing the sample size gives us a much larger level, gives us much larger confidence level. Finally, let's say suppose that the firm decided that it needed to have at least 96% confidence of the population mean time to within 1 hour. So how many people would the number of people in the firm surveys change, and why? So it says it should decrease because we have more information with a smaller sample, or it should increase. Well, again, I think we should increase right here. Let's just, again, let's check how Professor Peoples is doing here. Uh-oh. I marked the wrong thing, right? What did we say? I said the level of confidence. If we kept the error bound the same, the only surveyed people, what would happen to the level of confidence? Well, I said it would get larger. How is that right? Well, if we kept the error bound the same, but only surveyed 49 people, what would happen to the level of confidence? Well, it would be smaller. Why? we would have to have a smaller, lower level of confidence to keep that accuracy right there going, right? So in other words, our confidence level would be less. We would be less confident in that result. Hooray, okay. So there you go. Anyways, that should give you an idea right here, and I'm going to go ahead and stop the recording, which